Hi there, students. This is Dr. John, your physics professor. Today we are going to look at a range calculation. We're going to take an ideal projectile, whether that's an arrow as in my diagram, or whether that's a bullet or a football or a cannonball, anything that goes through the air in an arc like this and lands. So there's a couple of limitations on this. One is we're eliminating all ideas of air resistance. That's just not part of this equation. That makes it much more complicated. And we're shooting the arrow at the same height at which it lands. So this is basically a parabola, which is completely symmetrical around the center here. Those are the couple of limitations, and we're going to go through this calculation in these steps here. So I'll just write these out here for you so that you can see a clear sense of how you would do a calculation like this. By the way, if you want this as a download, I have this on my website, physicsdoctor.com. You can download a page that explains all of this, and you have it in your hand to use whenever you want to. The first step we're going to do is divide the initial velocity, that's v naught, into components, into x and y components, because the x component and the y component in these kinds of problems acts completely independently. The only force would be gravity acting on the y component, but the x component is independent of that. And then we're going to try to find the time of flight. We'll use the y component for that. And then we will take that time that we found and use that to find the range. And finally, we're going to put this into a proper form, although the form that we find at the end of part 3 here will be totally correct. We're going to put it into a more beautiful form, an easier form to use here in step number 4. So let's just take a look at this. We're going to start off by dividing this velocity into components. Let me just draw this up for you again. So here I have divided up your initial velocity into some components. The black one here represents the initial velocity at whatever angle you shoot it at, whether it's a small angle or a big angle. And then the blue here represents the x component, and the pink represents the y component. As you see, I put this would be the typical way that you would do this, and then you could add these components here. This would be vx, and this would be vy. You could say vx plus vy is equal to v0 or v naught. So each of these, this is a vector component, but it only goes in the x direction. This just goes in the y direction. This is the final vector component. This is how you would typically put them on a chart. However, we're going to move the pink vector over here. There's nothing wrong with putting the pink vector over there. However, it's much simpler in our calculation and for us to be able to see what we're doing by putting this over here. So I'm going to call this one here vy. Now we have something that we can use, an angle formula here with the sine and the cosine of this angle. I'll erase this here and then I'll draw this up for you. Let me start with the pink one here, which is vy. If you notice, this angle here, angle theta, would have an opposite and a hypotenuse. And if you remember from your definitions, the sine of the angle theta is the opposite over hypotenuse. Opposite being vy, and v naught or v0 is the hypotenuse here. So if we wanted to find just simply this one here, we would multiply both sides. I'll erase this here so it's not confusing. Multiply both sides by v0 like this. That gets rid of this. Now we have vy is equal to something. Let me write that up here for you, maybe right here so we can see it clearly. There you go. I've written this up here. This is the y component of the velocity. I'm going to do the same thing in blue for the x component. The x component is the cosine because that's the adjacent to this. So if you look at this, the definition of cosine theta is the adjacent over the hypotenuse. And for this angle, this is the adjacent. Remember, we have two adjacents, but the longest side, the side opposite 90 degrees, is always the hypotenuse. So this would be vx over v naught. Again, we don't need this middle term here. Let's multiply both sides by v0, like this. v0, and then we have the x component is equal to this, v0 times cosine theta. I'll write that right up here. There, we've now calculated the x and the y components in terms of the initial velocity and the angle theta. That's the first part that we've done here. If we had actual numbers, we could plug them in here, but in this case, we're just making a general formula that applies to all occasions. Next, let's look at the time of flight. For the time of flight, we're going to use the y component only, because when you think about it, the x component of the velocity, it's going to continue going on in this direction because there's no forces, there's no net forces affecting it. It's just going to continue on in this direction. The only force that there is gravity acting on the y force. So you might say, well, gravity is also acting on this x thing, but we're dividing it up into components. So the x component has no force that's acting in this direction. The gravity acts only on this direction here. So if you think about it, I'm going to stretch it out a little bit. This is sort of what the arrow would do. It would start off going up, it would go to a peak where the velocity would be 0, it would turn around and it would come back again. The initial y component right here going upward would be this. The initial y component would be this way. It would be v0 sine theta. That would be the initial component as we're going up here. And it turns around, hits 0, comes down again, and when it comes down and hits the ground, the velocity would again be v0 sine theta. Of course, it's going in a different direction. It's going in the negative direction rather than the up direction, but the amount, the quantity would be the same. So we're going to use that here to help make this calculation really easy. So let's take a look at that. Let's say that it hits the ground with this velocity, v0 sine theta. Now, if it hits the ground, it's going to start off here with an initial velocity of 0 and a final velocity of this, v0 sine theta. And what forces are acting on it? Well, the only force acting on it is gravity. The acceleration is equal to gravity. If you remember our simple equation, the final velocity of something would be equal to the initial velocity plus the acceleration times time. Well, there's no initial velocity if we're starting at the top and just dropping it. That's a trick that I find very useful in many of these parabola problems, in many of these range problems or other kinds of problems where you're trying to find the total height, is just turn it around and assume that you're holding this baseball or arrow or whatever at the top, drop it until it achieves this velocity. And it'll achieve this velocity. The final velocity is going to be equal to the acceleration times time, or the time is going to be equal to this final velocity divided by the acceleration. We can use that. I'm going to just erase some things over here. So the final velocity, if you're dropping it straight down, y component only here, is going to be this. So it's going to be v0 sine theta divided by what? The acceleration is gravity. So that's the acceleration of gravity. So that's the time from it to come from the top and drop to the very bottom where it's going to achieve this velocity, the y component of the velocity. That is half of the total time of flight. Because in essence, that's when it hits the peak here till here, which is the same as the time from here to here. So we take this time and double it to find the total time. So the total time would be twice this, 2 times v0 sine theta over g. I'm going to write that really small over here just so we have that available for us. And I'll write these things down here as well so we have them all on one side of the page. All right, I wrote this down here. I wrote down this, which is the total time, 2 v0 sine theta over g. And I wrote down these components, the x component, v0 cos theta, and the y component, v0 sine theta. So I've written these down. I can erase this side now, and we're going to get to our third part of this calculation. To find this time, this is the total time of flight. We calculated half the time and then doubled it to get the total time for this parabola. Use this time. So this is the time that it flies. The x velocity, of course, remains constant because there's no forces acting in this direction. The force acting in this direction affects only the y component. We can separate them completely. That's the whole purpose of doing this way. So the x component of the velocity, which is this, will continue on until it hits the ground. The only thing stopping the x component is when the y component hits the ground. In that way, they're tied together. The x stops when you hit the ground with the y component. So we can take the x component here. Here I wrote down the x component of the velocity. Always double check, make sure you do it right. v0 cos theta. And we can take the velocity and multiply by the time, the total time, which is this, 2 v0 sine theta over g. If you multiply these two together, you get the distance. Velocity times time equals distance. Distance equals velocity times time. That's if you have a constant velocity, and in the x direction, you have a constant velocity. So we'll multiply those two together. Notice what we have here. We're going to put them all together. We have a 2 in the front, and we have a v0 and a v0. So that's 2 of them squared. And we have a sine theta and a cos theta, all divided by g. That's a really nice equation. We're practically done here. I'm going to rewrite this one right up here so that it's nice and clear as we do one more modification on it. So here, notice I've rewritten this. This is the range. This is how far it goes. I've taken V naught squared, put it out front, put a G under it, just rearranged it a little bit. I put this 2 with the sine theta cos theta right here. So I've copied this accurately. This is the range. This equation here, perfectly valid for the range. You can use that one, but since we have complication of having 2 trig functions here for the angles, that makes it a little bit harder to use. Is there a way of simplifying that? Well, if you happen to remember or have a sheet of your double angle formulas, you're going to be using a lot of these in trig, so you might as well get used to being able to notice some of them. This is one of the double angle formulas. 2 sine theta cos theta is the same as sine of twice the angle. Here you have a single angle. Here you would have double the angle here. So we can rewrite this whole thing with a slight modification. So the range here is equal to V naught squared over G and then sine 2 theta. That would be put it into a proper format for the range equation. I'm going to take this range equation, write it right down there, and then just have one more thing to mention about it. Okay, I've written this range equation down here just so we have a copy of it. Always copy out the work that you do as you make progress, just so you don't forget what you did. I can erase the first part of this and just think through something for a second. This is a fairly nice equation for you to use. Remember when it applies. It applies when there's no air resistance, and it applies where what you're shooting off or throwing is at the same level as where it lands. If you're up on a hill, or if you're down in a valley, or if there's a hill or a wall over here, this exact equation won't apply. This is the range from the same height to the same height here. But it's extremely useful because if you know the initial velocity, G you know is 9.8, you just take the angle, double it, and get the sine, and you can get the range rather quickly. If you're going into an exam and you have this sort of in your head, you won't be given this in your test, but if you have this sort of in your head, you might be able to do 1 or 2 problems just with this here alone. It's probably worthwhile sort of reviewing a couple of times. Now let's notice a couple of things about this. You might wonder, how is it that we can get the maximum range? How is it we can go as far as we can? Well, we can't adjust V naught. That's however hard we're going to shoot it. Can't adjust G, but we could make this a maximum. So we want to know, when is sine 2 theta maximum? Well, the most it can be is 1. It could be +1 or -1, and it could be anywhere between +1 and -1. So 1 is the most this could be. What would we know about this? This angle inside here, everything inside here, the sine of 90 degrees is actually 1. The sine of 90 degrees is actually 1. So if we want to take half of that, that angle theta has to be half of that, then theta would have to be 45 degrees. So that means that the range is maximized for this ideal situation with no air resistance, and when you're shooting at ground level and landing on ground level, then theta, the angle that you shoot it at 45 degrees, gives you the maximum range, and the range would simply be this, V naught squared over G. So hopefully this helps you with this range problem, this very simple range problem, and walk through this yourself, rewind this tape, walk through this yourself, and see if you can do each one of these steps and get this answer fairly quickly. It'll be a great exercise for you. I will see you in the next video. Make sure to like and subscribe. Bye-bye.